Okay, so in this video today, what we're going to learn about is mass versus weight. They are different, and so it's super important to distinguish between the two of them. In the first video that you watched, it took you through sort of the idea of the big difference between mass and weight. We're just going to reiterate that, consolidate it, and then talk about some questions that are going to be related to it. Now, in a previous reading that you did, you learned about mass, weight, and volume as well. There was a reading that you did to talk about the difference between mass and volume, and weight and volume, and mass and weight. And then they brought in terms like density, things that you've learned before. And we're going to see how it all ties together. Now, the term weight, which I've bolded here, if you've got a highlighter, you might as well highlight it as well. So weight is the force of gravity acting on a mass. Okay, so mass is measured in kilograms, whereas weight is a force, so therefore it's measured in newtons. So mass is in kilograms and weight is in newtons. They are not the same thing. You should not interchange those words at all. And I guess I just wrote that. You cannot interchange the words mass and weight. They are different. Okay. One is a factor or a scale of the other one. All right. How do you write it? Well, again, these are vectors. We usually just drop them off because it just makes it easier. Now, what you're going to notice here is there's a symbol I've introduced, and you're like, what does that thing mean? If you recall back, F subscript G, weight, or F subscript G, is the force of gravity. That's what the subscript stands for, acting on an object. Hence, it's measured in newtons. Mass and weight are not the same. So here you've got mass. So the variable g is the acceleration due to gravity. It is approximately 9.8 meters per second on the surface of Earth, but it's different on different planets. So g changes depending on where you are. Now, this is just basically, if you remember back to Newton's second law, right? Newton's second law, I'm going to leave off all the net force, all that kind of stuff, but it said, basically the net force acting on an object is mass times acceleration. So since there's an acceleration of gravity, we call it g. You multiply by the mass. That will tell you how much force is pulling down on some object with some mass. So if I have a mass m here of an object, there would be a force of gravity pulling down that would be equal to m times the acceleration of gravity. And it's always pointing towards the object it's attracted to, in our case, towards the Earth. Now, the G, there's different ways of writing it. Some people write it A subscript G for acceleration of gravity, and other people just write it as G, like that. So it all depends on if you like A subscript G. It just gets a bit confusing with all the subscripts. So a common way to do it is to use G. Now, only on Earth or near the surface of the Earth. Remember, it changes actually even at different altitudes and different latitudes on Earth. This is near the surface of the Earth, the average. So this is the average near surface, only on Earth, right? Now, here's the neat thing about it. I wrote at the bottom here. And again, in that first video that you watched, it would have been fully explained as well. They talk through it. It says, recall from your reading about mass, weight, and volume, and inertia, that mass is a measure of inertia. And that was also in the video. So mass is a measure of inertia, or the resistance to change in motion. And the weight is a measure of the pull of gravity, okay? And so now we start to realize that this means that if you travel to the moon where gravity is weaker, in fact, it's only about 1.67 meters per second, the mass that you have will be the same. So you haven't changed your physical substance, like the amount of material that's in you, but the pull of gravity on you is less. So therefore, you would have less weight in newtons. If somebody came up to you and tried to push you over, they would still feel your mass. Like if they grabbed you and tried to shake you, it would feel identical to as if they were shaking you on Earth. You would have the same sensation. If you put a tank up on the moon, it would still be very difficult to push it. Even though there's less gravity, you could lift it easier, for sure. Maybe not a tank, but you could lift objects easier. But if you tried to accelerate them, physically try to accelerate them, it still takes the same amount of force to accelerate these objects.
Daddy,
Oh, Livy. Okay, so that was obviously my daughter. This means that if you travel to the moon, so we talked about that. So if you tried to actually move an object, if it was a heavy bowling ball and a rock, you still wouldn't want to walk up to the heavy bowling ball and kick it, compared to the small little pebble, because the big rock that you kick still has the same amount of inertia it had anywhere in the universe. And so therefore, it still is very resistant to change in motion. So it would still, if you tried to accelerate, it would behave exactly as if you tried to accelerate it on Earth. Now, because the force of gravity is less, friction would be less, and it's going to seem easier. And because it's lighter in terms of weight, you could hold it in your hand and hold it up easier. But if you tried to accelerate it, it's still going to feel very similar to accelerating a regular object anywhere in the universe. Okay, so let's try this out now and try a couple of little questions. So, first one. It says here, as an example, consider an astronaut that is now has a mass of 75 kilograms, calculating his weight on Earth and on the moon. All right. So on Earth, force of gravity acting on that object so it's 75 times 9.8, it's about 750, just less than 750. Because you're basically just multiplying it by 10. So 735 newtons. So that would be your weight on Earth. On the moon, you still have 75 kilograms of mass. You haven't lost any mass. You're still the same particles, but your acceleration is less. So you go 75 times 7 is you would only have a weight of about 125 newtons. So you'd be significantly lighter in terms of weight, but you would still have the same mass and the same inertia that you would normally have. So a person weighs 220 pounds on Earth. Calculate their mass in kilograms, where 1 kilogram is 2.2 pounds. Calculate their weight in newtons. So a person weighs 220 pounds. So 220 pounds. And we know that there are 2.2 pounds per kilogram. So that's going to leave you with, obviously 220 is just 100. So you have 100 kilograms of mass. And we're going to calculate their weight. So Fg equals mg. The mass is 100 times 9.8. And you don't need a calculator for this, but 980 newtons. So that would be the weight on Earth. Okay. Now let's say that you find an object and you're able to measure the weight of it in newtons, not in pounds. Now pounds is a weight because it's a force of gravity acting on an object, but it's an old system of units and we shouldn't use it at all, ever. So an object has a weight of 800 newtons on Earth. Calculate the mass of the person. So in this case, we're just isolating for m. So it's the force of gravity over g. And so m, the force of gravity is 800 newtons over 9.8 meters per second per second. And the units make sense because a newton is a kilogram meter per second per second. So the meter per second is divide out and you're left with kilograms. So 800 divided by 9.8, you're almost dividing by 10. So you know it's going to be just less, just a little more than 80. And it's about 82 or 81.6, about 82 kilograms. All right. So that's how you can go between the two of them. All right. Something else I want to point out is density. It's a big, very, 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 very important concept. And so density is the, mass and volume are not the same. Density relates mass and volume together. So what you're going to look at now is volume is the physical space that an object occupies. It could be measured in liters, milliliters, centimeters cubed, meters cubed, etc. And remember from your math classes that a milliliter is equal to a centimeter cubed. Okay. Mass is the stuff that makes up an object. Okay. And it's measured in grams or kilograms. And density is a ratio of the mass to volume. So it could be kilograms per meters cubed. It could be grams per centimeters cubed. It could be kilograms per millimeters cubed. It could be kilogram. It could be anything. It could be grams per meters cubed. It doesn't matter as long as it's a mass divided by a volume. The equation for it, again, this is, you did this in your previous years, probably in grade school and in grade 9. You've got density equals mass over volume. And so, or density equals mass over volume. So you've got that equation, and you just rearrange the formula as necessary to solve for whichever variable you're looking for. Okay. So remember, an object that has, if you have a big mass, so if your mass is large and your volume is small, then you have a massive density. Okay. If you have a low mass and a big volume, then you have a very low density. Okay. So here, this is high mass, low volume. So think of something that looks really small, and you pick it up and you're like, oh my gosh, this is heavy. It could be like a medicine ball. Whereas over here, you've got a beach ball where you've got a very low mass of the plastic, but a huge amount of volume, and it's got a very low density. So this is a low mass, high volume. Things like this, balloons have low density, rocks have high density. This is why rocks and all these sorts of things sink to the bottom of oceans, to the ground. We sink to the bottom of the air. But other things that have low mass and high volume will float to the surface of fluids and appear to float in water and that kind of stuff. All right. So now your activity is here. It's the mass versus weight and density. So you just obviously put your name on there, and you've got your equation. So sometimes weight is given the symbol W. Okay. 1 kilogram, if you have to convert between pounds and kilograms, that's the conversion there. And you've got your density formula. And G is the acceleration due to gravity. Again, you can write it as a subscript G. That is up to you. Okay. Now, write your mass in pounds. Okay. So we're going to write our mass in pounds. So you're going to do that. You're going to convert it to kilograms, calculate your weight on Earth, and then calculate your weight on the moon. Right? Just as a little consolidation on your own. Then you look down here, and we've got a 100 gram mass and another 100 gram mass. This one occupies a volume of 1,000 milliliters, and this one occupies a volume of 100 milliliters, and it's on a scale. Now the question is, which way will this scale tip? Which object is denser? Right? And so your example of the question. So which way would the balance tip? Which one do you think is a more dense object? Are they the same density? Are they less density? Is that kind of question. So you're going to answer that question and think about the problem very carefully. On the back, you've got the density of steel on Earth was found to be this. If you had a block of the object with these dimensions, you can find the volume. You can then rearrange the formula to find out the mass, and then you can calculate the weight of the object on a new planet where the acceleration is 5.4 meters per second. Okay, so you're just finishing up this sheet. I will post the solutions for that so you can check your work. And then you're going to do this further consolidation assignment on this work, which is super important to do. Don't leave any of this. Describe the difference between mass and weight. Be very clear. Show some equations. This is a consolidation piece. This is so that you can get yourself to write it again, figure it out, and then therefore consolidate it into your mind a little bit more. Describe the distance between mass and volume. You can use some examples. You might want to include the word density. So again, this is consolidation work. And then you're just going to answer these questions that are on the sheet. And again, I will post those solutions for you today. Okay, good luck with the work. Sorry about my daughter jumping in there.